Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. Hi everyone. It's my great pleasure to introduce Sarfaraz Khurshid, who is from UT Austin. And I'll give him the floor right away. He's going to talk to us about assertion-driven error recovery. Thank you, Sarfaraz.
Okay. Thank you, Patrice. Okay, so yeah, I'll be talking about assertion-driven error recovery. So we'll talk a lot about different ways of using assertions in this talk, and I'll focus on how you can recover from errors using assertion violations. So this is a talk about finding bugs, as you, I'm sure, aware of how they look like. This is how they looked like about 50 years ago, but they still bug us quite a bit, and they create lots of problems for us. We are trying to develop new techniques which can help us get rid of bugs. They don't look quite like this anymore, but they still are there in software. Bugs have had a significant impact on the quality of software, reliability, as well as the cost of producing it and maintaining it. And it's because of bugs that if you look at some of the warranties that you get with software, they don't say too much. So here are some sample warranties taken from some survey that was done about 2 decades ago. I just wanted to start on some lighter note. So here's some fun stuff. So this thing says that Cosmotronic Software Unlimited Inc. does not warrant that the functions contained in the program will meet your requirements or that the operation of the program will be uninterrupted or error-free. However, they do warrant the diskettes on which the program is furnished to be of black color and square shape and normal use for a period of 90 days. That's a pretty nice thing to say, that, at least, some of you might not have seen any diskettes like this, but those of us who are old enough, we used to work with them. And they were not all that reliable. Here's another one. It says we don't claim interactive easy flow is good for anything. If you think it is, great, but it's up to you to decide. If it doesn't work, tough. If you lose 1 million because it messes up, it's you that's out of the million, not us. If you don't like this disclaimer, tough. We reserve the right to do the absolute minimum provided by law, up to and including nothing. This is basically the same disclaimer that comes with all software packages, but ours is in plain English. We didn't really want to include any disclaimer, but our lawyers insisted. We tried to ignore them, but they threatened us with the attack shock, at which point we relented. So this is what was there, like in 87. So what about 2008? Maybe things are much better. Well, here's something that Apple tells us. They wanted the media on which the Apple software is recorded and delivered by Apple to be free from defects for a period of 90 days from the date of original retail purchase. And the software is provided as is with all faults without warranty of any kind. Maybe Google is better. It's provided as is with no warranties whatsoever. Here's a third one, but let's skip over this one for now. The bugs are still there. They create problems. My students and I are working on the basic question of how do you deal with bugs. So if you look at existing approaches, there are several methodologies that exist today, and these methodologies apply during different stages of the development life cycle of a product. For example, there are techniques that allow you to do better design. There are techniques that help you code in better ways, and there are techniques that can test your programs in somewhat automated fashions. There's a lot of work on runtime checking, error recovery. However, most of the existing methodologies have one thing in common, which is kind of an issue, that if you look at methodologies that apply at different stages of development, they typically require fundamentally different approaches and algorithms. And moreover, there typically is no synergy which exists among methodologies that apply at different stages. And if you want to apply a combination of methodologies, which you could do, the cost for doing that is typically at least linear in the number of methodologies used, and which means that checking is usually done very late in the game, and by that time it might just be too late and the reward might be too little. So one of the motivations we have is to see how you can take different methodologies that apply during different stages and apply them in a uniform fashion for much less cost than having to apply them individually. one of the projects we are working on is based on assertions, and we are exploring this notion of assertion-driven development, where the basic insight is that you could use assertions as a basis of a holistic approach that enables an application of several of these methodologies in synergy. And I'm sure everybody in this room is familiar with the notion of an assertion. The simplest example is that of having some check in the program which says something like x is bigger than 0. But the assertions I'm talking about are much richer than those simple ones, and I'll show you several examples. There are various, mostly well-known benefits that assertions offer. For example, they tend to be culturally acceptable. If you look at what form of specifications the developers are most likely to write, if any, it may be assertions. You can make them much more attractive by rethinking them a little. And one of the nice things about assertions is that they provide a flexible intermediate point between full specifications and no specifications. So you can specify as much as you want or as little as you want, and in a way they provide an ideal vehicle for making specifications attractive to developers, because you can ask them to write minimal assertions, then you provide them some tool support, and as they see like the benefits of asserting their code with specs, they can write more and more. Also, indeed, an assertion is simply a lightweight specification that you can write using the underlying programming language. So what that implies is that you can teach assertions at the same time as programming. And typically in teaching, it's often a problem that you first teach them how to write code and then talk about specifications, so they naturally tend to write code before they write any specs. But you can teach them about assertions at the same time as you teach them how to program. So using the assertion-driven development, we are building various analyses, and our vision is to have a much broader use of assertions, where you could specify properties of code as well as perhaps some detailed design constraints. You could enable deep semantic static checks. You could enable systematic testing, as well as runtime checking and error recovery, which will be the focus of today's talk. Our work builds on various existing approaches. As I said, assertions have been used for a long time, and there are many languages who have had assertions in one form or perhaps a richer form. For example, IFL's designed by contract, or ESC Java, JML, Spec Sharp. The key difference between previous approaches and ours is to enable a whole spectrum of analyses using the same assertions that the developers write once, which means that the cost of writing such assertions will be paid back several times over. So this work is done by my students. Here is a slide which introduces them. For example, I've highlighted the ones who made a significant contribution to this project. Basim is over here. He's interning here. I've also had a couple of students graduated who work full-time at Microsoft. And this project started when Yuklai was doing his master's thesis with me. And then Khalid also did some work on repair with me. And Ivan Garcia I've highlighted because he also contributed significantly, but he is the only one who worked on repair with me and is not currently working at Microsoft. Okay, so to give you an outline of some of the projects that we have or the thrusts we are working on in terms of assertion-driven development and analyses, we are working on analyzing designs. So a basic question over there is, how do you analyze properties of designs? We developed a new relational encoding for solving alloy formulas, which can specify properties of software designs. So if you're familiar with alloy, you'd know that it translates first-order logic to SAT and then uses off-the-shelf SAT technology to find solutions or check properties. We instead translate it to netlists or sequential circuits, which have been widely used in hardware verification, and the results showed that we could get far better analysis than off-the-shelf SAT solvers by translating to netlists. And the sort of intuition there is, when you translate first-order logic formulas, which pervasively use quantification and transitive closure, and you go down to SAT, you have linearized the formula too much, and you have lost a lot of the structure that exists at the high level. And when you translate to netlists, which resemble really simple C programs where the loops are bounded, the translation is much better, and then you can do a lot of transformations which hardware community has developed over a few decades, and they minimize the resulting formulas which allow much better and faster analysis, which scales a lot better. We've also developed some techniques for declarative slicing, where the idea is when you want to solve a formula, let's say a SATS formula, you don't try to give the whole formula to the SAT solver and let it go away and find a solution, but instead you partition it, or you prioritize the constraints within the formula, so that even though you want to solve the whole formula, you don't solve the entire thing at one execution of the solver. And we are also doing some work on checking code as it is developed. So when you write some small module, how do you do some static checking of the code by translating it into a, say, a formula which you solve using a SAT solver or a sequential circuit solver. And for testing, we are pursuing various threads. One of them is constraint-based generation, which I've been working on for several years now. Then we have also recently explored staged generation, where the idea is that you don't generate all the inputs for a module at the same time, but you prioritize them. Once again, use some notion of constraint prioritization, and that way you can generate much bigger inputs much faster. We've also explored the use of parallel algorithms in test generation as well as execution. So now that you have clusters of commodity machines available, why not make use of them to check properties of your programs? We've also explored some ideas from white box generation together with the traditional black box testing stuff we were doing. So the focus of this talk is on error recovery, where the basic question that we address is how do you repair erroneous program states, and we use violated assertions as a basis of repairing. And I'm going to be focusing on this last thread in the rest of this talk, but we basically use assertions to unify all these checks. And one of the reasons I picked error recovery for this talk was because it tends to be usually a lively topic to present and for discussions. And also because I have people sitting in audience who worked on this, so I have enough defenses against any attacks you might have. So here's the outline of the rest of this talk. I'll give you an example of what repair is, and then I'll describe some background. I'll describe our approach to it, and with a discussion. And of course, please feel free to ask questions at any time, and that'll make it much more interesting for me to present. Okay, so the basic question in error recovery is how do you deal with erroneous program states? So the context here is that we want to repair broken data structures in a program. And if you look at programs that manipulate data structures, they often assume some consistency properties of their data structures. For example, if you look at HSQLDB or some other database implementation, it would assume that the data internally is perhaps stored in an AVL tree or some other balanced binary search tree. And then bugs or some other external events could corrupt the data structures, which means there's a violation of some consistency assumptions and the program cannot continue correctly, and that can lead to unpredictable program behavior. So the basic insight we have had in this work on error recovery is that often there is some redundancy in the data structures that you could use to repair them. An example of such redundancy is that you might have a field which caches the number of nodes in a structure. So even though you can always count the number of nodes by traversing the structure, you have this redundant field which stores the number of nodes. Now if this field gets corrupted, you could traverse the tree, for example, and fix the value of this field. I will give you several more examples of where this such redundancy happens in commonly used data structures. So let's make this notion of corruption a bit more precise. Here are some concrete examples. The first one is an n-ary tree. It's an acyclic data structure. Here we have a singly linked list, so these are the next pointers. Here we have a binary search tree, so it satisfies acyclicity as well as various other properties including search constraints, which means the values in the left subtree must be smaller than the value in a node and the right subtree must be bigger and so forth. So an example of a corruption is that in an in a tree or an acyclic data structure, you get some illegal sharing of nodes, or perhaps you get some directed cycles which are not allowed. Another example is perhaps the value of the size field gets corrupted, so you have some inconsistent data fields. The example over here is perhaps the nodes are not in the correct search order and need to be fixed. Okay, so how do you write assertions that can let us repair such structures? Well, you can use assertions quite easily to define data structure consistency properties. For example, you could write a Java predicate or a method which returns a Boolean value. It traverses the structure, returns true if the structure satisfies the constraints, and returns false otherwise. And in such a case, an assertion violation indicates a corruption in the program state. So here's an example of how you may write one such method. Here's a class that declares a singly linked list. Every list has a header node, a size field. Node is an inner class with the next pointers. And here is our predicate, which traverses a given structure, returns true if it satisfies the constraints, which are also called the class invariants, and returns false otherwise. Here's how you could write such a repo K. It's a very standard visited node based algorithm which starts at the root of the list. If that's null, then size should be 0. Otherwise, we build a set of visited nodes. Then we have a while loop which looks for the last node, and until you find that, you add every node you visit to the set of visited nodes. If you ever add the same thing that was there previously, you return false. Otherwise, you move your temporary pointer into the list until you hit the end of the list. And the last thing you do is you check that the value of the size field is the number of nodes that you visited. So that's an example of how you can write a check for acyclicity for a singly linked list. So here is how an assertion-based repair approach differs from the traditional approach of using assertions. So here's a piece of code that expects this object to be acyclic at this point, because what it's going to do is it's going to go into a while loop looking for the last node, and so it's looking for a null pointer, null terminated list. But maybe if there's a list has cycles, so this loop will never terminate, so there's an assertion which checks that the list is acyclic. And in such a case, if you give it the following data structure, I'm sorry about confusing the colors, but it has a directed cycle which goes in this direction, the loop will keep going forever. So in this case, when you check the assertion, if the assertion is true, you'll continue on with the rest of the code. Otherwise, if the assertion is false, you will terminate the program, throw an assertion violation exception, debug the program, and perhaps re-execute it. However, in our approach, which is the repair-based approach, the idea is that you take the mutated structure, you check the assertion. If it's true, that's fine. You do nothing. The behavior is the same as before. However, if the assertion is false, you basically repair the structure using this assertion as a basis of repair. And you transform the assertion into a repair engine, and you do mutations of the original structure. So the difference between this figure and this one is that we have broken this link here, which was causing a directed cycle in here. So now this structure is acyclic, and you let the program continue to execute. Okay, so now I'll give you another example to show how repair works. So here is a doubly linked circular list. These are commonly found in libraries. And over here we have a header node, and the size of the list is 3. The header is considered to be a sentinel node, so an empty list will have a header whose next and previous are just pointing back to itself. And then every node has a next node and a previous node, and there are various properties. One is that circularity along the next pointers, circularity along the previous pointers, previous pointing in the reverse direction of next, and so forth. So here's a class declaration for the doubly linked list. We once again have a header entry size, and then entry is an inner class with some elements, and then next and previous pointers. So here's a method which adds incorrectly to the beginning of a list. It takes an input, O, and then it tries to allocate a new node which is going to go at the front of the list. So can someone find what the error is in this method? For those of you who saw this at ICSI, please don't. Okay, let me help you a little. There are 2 errors in this method, and these are the statements where they are. So remember, one of the properties was that next and previous should form this sort of a transpose relationship. Okay, let me give you another hint. So we are setting e's next to t. So who should be t's previous? Very good. Otherwise what's happening is all the previous pointers are just pointing to the header. So what's the problem here? It's an empty line, but that's not really a problem. There should definitely be something there other than the comment. Okay, let me give you another hint. It's not about the linking structure of the list. Thank you. So we have this field called size, and it's never incremented after you add the node. Okay, so if you take a program like that, you add these 7 elements in there, you get a structure which looks something like this. All the previous pointers point here, size is always 0. And if you apply our repair technique using the class invariant for a doubly linked list, it repairs it correctly to the following structure. Okay, so that was the example. And let me go in some more details of repair. So what does it really mean to repair? Well, conceptually, the idea is that here is this whole class of structures which don't satisfy your structural invariants. And here is this class of structures which do satisfy your structural invariant. So what's happening is we are given some guy in here, and we want to map it to some sort of a similar looking structure in this class which does satisfy the repo K. Okay, so this is the game we are playing. And right now, all we are given is this assertion, which basically is the class invariant. But I will talk about how you can get richer assertions that can talk about stronger properties than just class invariants, and you could use them as a basis of repair. So here, one very basic thing is that we'd like to generate a similar structure. Of course, like in that linked list example I showed you, if you just give me back an empty list, that's repaired, it satisfies the class invariant, but that's not such a useful list. So maybe you want something better. For example, you want something that preserves the reachability of the data elements. So that's one of the heuristics we use in our repair algorithm, that we do try to preserve reachability, but of course you can write an assertion in a way which says, okay, I just want 3 nodes in the list, and then there's no way you can preserve reachability if you started with 4. So we need to keep in mind that this notion of similarity is kind of heuristic, and it is possible that in the worst case the repaired structure is very different from the original one, but I will discuss in the end how we are trying to make this notion of repair more precise. And just to give you an idea, you could specify how you want the repair done using some notion of assertions which is very similar to post conditions, which relate the state of the structure before the repair to the state of the structure after the repair. And here's an example of such a post condition, which says that if you look at the set of the elements reachable from header following 0 or more traversals of next, that set of elements in the post-repair state should be the same as the set of the elements in the pre-repair state. Okay, so this tells what are the things that you'd like repair to preserve. Our tools do not currently support assertions which are this powerful. They only support assertions which apply to one program state, which is similar to the notion of a class invariant, whereas this is very much like traditional post conditions. Okay, so here's the overview of the repair algorithm. It uses the violated assertion as a basis of performing repair. What it does is it executes that method or your assertion and monitors its execution to isolate a component of the structure that is necessarily corrupt, and it must make some mutations there for the structure to become overall correct. The mutations are based on a systematic search of a neighborhood of the corrupt structure, and we use symbolic execution for data fields that need to be repaired, and I'll show you some results on its efficiency and effectiveness. Yeah.
Can you define what you mean by neighborhood?
Say that again?
Can you define what neighborhood of a structure is?
Yeah, I'll show you an example, and basically it's a systematic search, and it's a bounded systematic search. So one example of neighborhood is that you can say, I don't want to perform more than 5 mutations on the structure. So all the structures that are sort of within 5 mutations of the given one will be the neighborhood. So you can control the neighborhood as a user by limiting the number of mutations that are performed on the corrupt structure. Okay, so I'll probably give a little bit of introduction on symbolic execution, although it's not all that integral, but we do use it for repairing data fields which might have become corrupted. But let me just give you an example rather than going over that slide. So here's a program. This is a technique developed 3 decades ago at least. And it's become really popular these days because now the constraint solvers are much more efficient than they used to have 30 years ago. So now we can actually do symbolic execution on realistic programs. So here's an example of a program that takes 2 integers as inputs and then compares them, does some computation, compares them again, and here you assert false. So let's see if we can get there. So just to make sure that we understand what execution is, here's a concrete execution path in the program. Let's say we start the program on values x is 1 and y is 0. So when you run it on concrete values, you follow one particular path in the program, and unless there's some non-determinism which we are not considering over here. So the first thing you do is you check whether 1 is bigger than 0. It is, so you go in the body of the if statement, if branch. You perform the updates on the variables. And at this point, what you have done is you have swapped the values of x and y, and now you check again whether x is bigger than y, which it is not, so the program terminates. So that was an example of a concrete execution. In symbolic execution, what you do is, the only thing you can assume about the symbolic inputs is that they are perhaps 32-bit integers. But that's all you know about them. So you start symbolic execution using symbols as inputs, and you do algebraic manipulations when you are doing computations in the program. So the first thing was to check whether x is bigger than y. In this case, since you don't know anything about, all you know is that x and y could be any values, we are going to explore both branches. In one branch, we assume that x is no more than y, and in that case, the program just terminates. In the other branch, we assume x is bigger than y, and notice that we are noting down these assumptions into what's called path conditions. So we write down the assumptions, document them somewhere, because they tell us what are the conditions on the inputs that must be satisfied to get to a certain path in the program. And then when we do updates on programs, we basically do algebraic manipulations. We could do some simplifications if you want. And at this point, notice once again that you have swapped the values of x and y, and now we check again whether the variable x is bigger than variable y. So one possibility is that you have the new path condition, which includes the second check, which says x is bigger than y and x and y is no more than x. And the other check is for going inside here, it requires x to be bigger than y and y to be bigger than x. And if you have a constraint solver which can determine feasibility, at this point you'll know that that's not feasible and the program will terminate. So that's what the basic idea behind symbolic execution. You start with symbolic variables, do symbolic manipulations, and keep track of path conditions. Okay, and this was developed a long time back. So here are some more details of our algorithm for repair. So let's say you want to repair a structure S. We execute the assertion or the repo K, class invariant in this case, and monitor its execution. We note the order in which object fields of the structure are accessed, and that's very important for systematic repair. When the execution evaluates to false, we backtrack and modify the value of the last field that was accessed. And the way we modify is we modify it to a different value, which for a data would become just a symbolic value, which is not equal to the original one, and then we re-execute repo K or the assertion. And the basic idea of like monitoring and backtracking on the last field accessed is essentially the same as what we had in Korath algorithm for test generation. So here is how we handle a reference field. Make a non-deterministic assignment to null. And another possibility you try is an object of a compatible type that you have already encountered in the traversal down the structure so far. And the third possibility is you try non-deterministically the objects that you have not visited so far following the traversal from the root. And for a primitive field such as size, let's say it has originally a value v, you assign it some symbolic value, and then you add to the path condition that we want a value different from v to fix it. Here is an example of the algorithm. So just to remind ourselves, this is the doubly linked list declaration we saw. There's a header node, size, and then every entry has a next and a previous. So here's the repo K for a doubly linked list. This is a slightly longer assertion. but it does return true or false. So the first thing it checks is if the header is null, it just returns false because we expect an empty list to still have a header node which has a sentinel value, and it should have size 0. And then this is another visited set node based algorithm. We first add header to the set of visited nodes, and then we have 2 pointers into the list. One is called the current, the other one is called the next. The current starts at header, and next is always the next pointer for the current. So if we ever see a null next, it should not happen because these lists are circular. So you should never have a next null pointer, you return false. Otherwise, if you ever see that the previous of next is not current, you return false. So this is checking the transpose relation between next and previous. And then you move the current pointer forward. And if you ever see a cycle in the list, you get out of this while loop, and you only expect there to be one cycle in the list that contains all the nodes and should go all the way back. So you check whether you have come back to the header node. If not, you return false. And the final thing you check is that the number of nodes you have visited should be one more than the value of the size field, because the first node is just a sentinel node and its value doesn't matter. Okay, so let's say this is our assertion. Here is an input on which we execute it. This is not a valid doubly linked circular list because this edge is in orange, but actually it's not just because of the color, but it should be pointing back here to E1 rather than pointing back to itself, so that there is a circular relation there. So when we execute this method, if you recall, what are we going to do? We are going to monitor the execution. And in particular, we are going to build an ordering in which we access the object fields of the input. So the first field we access is the header, the header field of the list. So we write down here that we have accessed, let's call the list object L0. We have accessed the header of L0. The next thing you access is the next field of current, which is this next field. So we document here that we have accessed E0's next. And after that, we access the previous field of next. So we have accessed E1's previous. So we write down that here. And then we go in the loop once again. So we document that this time we are accessing E1's next. And everything is fine so far. But once we access E0's previous, in this check, that's not current because current was pointing over here, and at that point we return false. So we build this list of field accesses that we have made in the data structure, and now we are going to backtrack on the last field that was accessed.
So,
yeah.
So this is through symbolic execution?
No, this is through, this is concrete execution on this input, but just by monitoring the execution of the thing. So we basically, this is how we've been doing so far. We would instrument this program so that all the field accesses, like here or here, all of them become method invocations. So whenever a field is accessed, some observer is notified that a certain field is accessed, and then that guy builds this list of field ordering. Yeah.
I was just going to ask how you do it for this method, because visited is going to touch a lot of fields as well. But here, you instrument the body of repo, okay, you said?
Yes. And the nice thing is that everything that's going inside visited, everything is concrete. Yeah.
So far, in this example, no symbolic execution yet?
No, none yet. And actually, I carefully kept size to be 1, which is the correct value. So if it were 0, then at this point, we will make size symbolic when this return false would happen. But so far, the only thing that's wrong is the structure of the linking structure, and we are returning false over here.
So this symbolic execution is done statically or while running, at runtime, so to speak?
Well, the instrumentation is done statically, but then initially the things are that you have the concrete values, but then once you need, it becomes a symbolic value. Yeah.
So how do you maintain the reachability information you're talking about? Because just modifying the last value is not guarantee that you maintain reachability to all nodes.
Okay, yeah, that's a very good question, and that's a different question. So right now I'm presenting the very basic algorithm, which can break the reachability. But then, yeah, we have a later version, newer algorithm, which does compute the reachability a priori, and then only reuses the nodes that were reachable originally. Yeah. So this is the most fundamental algorithm. Any other questions? Okay, so we have built this ordering in which we are accessing the fields, and now we are going to backtrack on the last one. So here's once again the broken structure, and you can view this structure. Here's the linearization of the structure if it makes it any easier to see how the backtracking is done, where for the list object we have two entries. One is for the header, the other one is for size, and header's value is E0, size is 1, and then for each entry we have a next and a previous. I'm skipping the element here for simplicity. So the next of E0 points to E1 and previous is E0. So when we backtrack, if you recall the non-deterministic assignment, the first thing you're going to try is null if it wasn't originally null. So in that case, we backtrack on this thing and we try null instead of E0. You get a structure which looks like this, where the previous now is set to null. And this does not satisfy the rep OK either. So we are going to execute the rep OK, come back to that return false, and then backtrack once again and continue on with the non-deterministic assignment. So when you backtrack once again, now you'll try another of these entries as a possible value, but you won't try something that you tried before. So the only thing we are left with in this case is E1, and when you set E0's previous to E1, in this case you do satisfy the structural constraints. So in this case you had to backtrack twice in order to fix it. Okay, and at this point the structure does satisfy rep OK, but assuming the value of size was wrong, what would happen is we would actually return false over here, and then we'd add a constraint that size should not be 0, and then symbolically we'd know the exact value because the value of this expression is a concrete value. You know how many nodes you have visited, you subtract 1, that's the value of the size, and that's what you'll modify size to. Okay, any questions about this repair step? So that's the core of how the repair algorithm works, yeah?
So your pointers are not symbolic?
No, the pointers are not. And this is what Korat does. And in Korat we did not have symbolic pointers, because the idea is that in Korat what you're doing is you could build constraints symbolically, but then you still have to solve them. And in Korat what you're sort of doing is you're solving them on the fly. So you're exploring, using this non-deterministic assignment, you're exploring the different possible values you could have.
So if the linked list had like 50 elements, you would have tried a lot of things.
Excellent question. So if the linked list has, let's say, 5,000 elements, you could have tried 5,000 different things for this previous before you got to the correct one. And then that's where one of our optimizations come in. So we had this is our basic work on repair. So we had a follow-up paper at UPSLA last year where we did certain optimizations, and then we would actually do some partial building of constraints on pointers, and that was sufficient to actually in one step repair the pointers. At least for the local constraints, which you can check locally, it makes a lot of sense to build these symbolic representations. But then there are these global constraints like balance of a tree. So the symbolic constraints over there are much more complex.
So why not just make pointers symbolic? Then you can.
Your formulas become big, and then in the end still you need some constraint solver. So what's happening here is like it's solving them on the fly.
So here rep OK can be arbitrary code.
Yeah, this is arbitrary code.
And you don't fully symbolically execute rep OK.
No, actually we would not symbolically execute anything unless we had some data field that was corrupt. It would all be
You don't need to symbolically execute your rep OK. You still have a concrete data structure. Just at some point of view, values are symbolic.
Yeah. You can build some constraints. Yes. Yeah. Yeah, you could, and then it resembles, for example, the idea of Dart very closely if you're doing symbolic over there. Yeah. Okay, so we have some implementation, and it has three main components. One is the search component, which implements this backtracking using re-execution. So we on every candidate structure we execute rep OK from the beginning. We don't do, for example, state storing and then then recreating the states and doing backtracking in the like stateful model checker would do. But we do something which, for example, a stateless model checker would do. There are some library classes that implement symbolic execution, and one thing we observed was that the set of benchmarks we used, they typically had very simple constraints on integers. So then Bassem implemented one of his own constraint solvers we call DCOS, and it solves basically linear integer constraints, and those are very efficient to solve. So for these binary search trees and stuff, you don't need to use any fancy constraint solver that handles a large class of constraints, but you can do really efficient solving if the constraints are really simple in nature. Okay, so we have various optimizations. For efficiency, there are some heuristics. For example, if you expect that your data structures will have only a few corruptions, you can set the number of field mutations that the tool is going to perform, and you can basically set an upper bound on that, and then that defines the neighborhood of structures you'll consider. For effectiveness, we try and preserve the reachability of data values, and also we provide some we support abstraction functions which allow you to compare pre and post repair structures. So what happens at the end of the repair is that it generates these repair logs, and you could provide your own abstraction function. For example, your abstraction function might just be that just count for each type involved in the data structure, tell me how many objects exist before you do the repair, and tell me what happens after the repair. So that's an example of an abstraction function. And we have a tool which I'll give you a link at the end, and it is downloadable and supports those abstraction functions. Here's a table that gives you some idea of the performance. So we have a bunch of data structures, singly, doubly linked lists, binary trees, some red-black trees, disjoint sets, and then we also looked at these two data structures from applications. Intentional name comes from the intentional naming system, and those of you who were at Microsoft Research in 2001 might remember I presented a talk on checking and analyzing and correcting the implementation of the intentional naming system. It's the same thing. We have been using this example for almost 10 years now. And then this relational database is HSQLDB, and these are AVL trees, which are the internal data structures of HSQLDB. So in typical cases, we could repair structures with a few hundred nodes. These times are in milliseconds, and the different columns are the different number of errors we injected. So 1 error, 5 errors, 10, 15, 20. So we kept the number of errors too small because that's kind of, at least in the scenarios we looked at, the realistic situation, because if the corruption is happening due to some external event, you don't expect everything to get corrupted, and everything is corrupted, then there's very little you can do about that. Or if this is due to some bug in the program which you did not find, and now this and you did systematic testing, but now this bug has appeared in production, then maybe the bug has only corrupted a few parts. But you can see like how the thing is growing. So clearly, like, you are not going to be able to repair structures with 20,000 nodes with 15,000 faults. That just is not going to make sense. But if you have a small number of faults in the structures, you can sometimes repair stuff with a few hundred nodes within a second or so. But this is the performance of one of the basic algorithms we had. And then we had some optimizations, which I'll very briefly describe in a bit, which allows us to scale to an order of magnitude larger structures. And those optimizations include doing some static analysis on the repo K, and then using the information from the static analysis to prioritize the repair actions, so that for different kinds of fields you're making the non-deterministic assignment. You've changed the order in which the non-deterministic assignment is going to happen. So that gets us to this discussion section. Let me just skip over some stuff and get to maybe more interesting stuff. So this is the static analysis where we used Cahoon and McKinley's recurrent field analysis, which tells you, given the repo K, it tells you which of the fields of the data structure are what they call recurrent. And recurrent fields are those which the program uses primarily to get to the data in the structure. So for example, if you have binary trees with parent pointers, left and right are the recurrent fields, and parent is not a recurrent field. So by using the recurrent field analysis, we were able to prioritize repair actions differently based on whether a field recurs or not. And that allows us to scale much better. And another recent project we worked on was to do constraint-based generation of larger test inputs. So if you're familiar with the work we were doing several years ago on Testra or Korath, there the idea was to do this bounded exhaustive testing where you generate a large number of small inputs. But that small meant really small, like 10 or maybe 12, maybe 14 was the max we would ever get to. What if you want to take this constraint and generate a graph with 10,000 nodes which satisfies the constraint? The traditional approaches, at least the ones that we had, do not work in that case. So what we did was we introduced the idea of using repair as a basis of generation. So the idea there is that you basically identify concerns of generation and you solve for them separately. So if you want a large graph, one of the concerns is that you want a large graph. If you want a graph with 10,000 nodes, that's what we try and do first. We start with a graph of 10,000 nodes, which is generated at random. It's really easy to generate a graph at random. And then if you want the pointers to satisfy some structural constraints, okay, we'll repair that graph, which is most likely not currently satisfying any constraint that you want, and then we'll repair it to satisfy the constraints. And then if you also have some data constraints on the values, we'll solve for them. So this way you sort of prioritize how you are going to solve for various constraints, and that allows us to generate fairly large graphs. So another related project which Khalid did, who's sitting over here, was on using these ideas of repairing program states to repair actual program implementations. So if you notice what's happening is you are changing the values of certain fields. But now for each repair action, if you monitor where the local variables of the program are pointing to on that graph, you could translate repair actions into code which does actually compile with your program and performs the repair actions for you. So that was his master's thesis, and we haven't extended this work much more so far, but hopefully we'll do it soon. So here are some of the ongoing / future stuff along the lines of repair that we are working on. One is to basically formalize this notion of repair a bit more. So in particular, perhaps define a similarity metric and then say that the repaired structure is one that you can generate using a minimal perturbation with respect to some graph difference metrics. So in particular, you can view these structures as object graphs. You can use some results from standard graph, mathematical graph theory to define a distance between two graphs. And could you generate a repaired structure that's closest according to some metric? Another thing we are looking at is to support stronger assertions, like the ones I showed you, which relate pre and post state, and that is very nice because it can allow you to enable customized repair solutions which are written declaratively. So the user does not have to implement a repair routine themselves, but they write this post condition like assertion, which is typically much easier to write than to actually implement a repair routine for some data structure. And we are actually looking at using Alloy and Quadcard for doing this, because Quadcard is one of the newest backends for the Alloy analyzer, and it turns out to be doing very nice and optimizations for rewriting formulas before sending to the SAT solver. So in particular, it can exploit things which are constant. And if you look at those formulas which relate pre and post conditions, the thing that talks about the pre-state you already have. So it's only that you have to solve for the post thing. And we are looking at using Quadcard for these richer assertions. Another thing which I find very interesting is to really characterize certain bugs that are so-called repairable. So for example, is it true that a repair algorithm can fix any corruption of a non-recurrent field, assuming that the recurrent fields have the correct values? So what that would mean is you do this recurrent field analysis on your program, and you know that as long as your mutations of the recurrent fields are okay, it doesn't essentially matter like how you were updating the non-recurrent fields. There's enough redundancy in the structure for the repair to actually fix it. And we don't know whether this is true or not. Also, of course, we are looking at its applications in fault localization as well as program repair, perhaps to suggest bug fixes to the user, because once you synthesize repair actions into program statements, those are your suggestions for possible bug fixes that the user might make. And indeed, we are looking at evaluating it on more realistic, larger applications. So if you have some, we'd be more than happy to look at them. Yeah?
Is this the right time for a question?
Every time is the right time.
So you're making a strong assumption that at any point of time, you take a repair action on the last entry that you visited. Is that right? Now, does that have some, is that assumption correct basically? Is there a possibility that first of all, that creates a dependency on how you write your replica, and the order of the checks that you put in the replica becomes significantly important.
Yeah.
And is there an algorithm for that? Is there any rationale behind?
Okay, yeah, that's an excellent question, and that points to a very fundamental property of this basic algorithm that I showed you, that it depends, as you said, on how you write the repo K. For example, you can traverse everything, set some Boolean flag somewhere, and return the value of that flag. And that's okay as well. It'll just make the search very slow. So you'll still systematically explore all the possible structures in the bounded space, but it'll be much slower. So the idea is that you write these repo Ks or even these assertions, and that's how you would naturally write them. You want your assertion to evaluate to false as soon as possible. So you tend to write them in a way that they short circuit as soon as you determine that something is wrong. And as long as you do that, at least the experiments we did, naturally written repo Ks would give reasonably good results. And a second aspect of that is that if you use something like alloy or cod, which translates to SAT, so in this case, at least our intuition is that the translation will be more robust to the way you write the formulas. And in particular, I don't know how to write a constraint using alloy so that I can force the SAT solver to explore every possible thing in the state space. But I do know how to write it in Korat to force it to explore every possible thing. So the translation to SAT might turn out to be very interesting in the sense that it tends to be more robust against badly written assertions.
So, for example, if you have got a binary tree, let's assume you've got a problem in there, you've got a cycle. Let's assume we write the assertion in such a way that it first checks for, instead of first checking for cyclicity, it checks for consistency, meaning that all the, you got 1, 2, 3, 4, 5, 6, 7, 8. Now, because of the cycle, your consistency is failing. Now you're going back into repair functions and trying to maybe modify data, whereas you're supposed to be checking the cycle first.
Yeah. Okay, so the way you mitigate that situation is, and actually I don't have the tool installed here, but our tool allows you to set some fields to be unmodifiable, and then they will not be changed. For example, you might want to say that I know for sure that the size will not get corrupted because it's very easy to maintain. I always update it. In add, I increment it. In subtract, I decrement it. So I know that size is correct. So you can set size as unmodifiable for the repair routine, and it's only going to change the fields that you allow it to change. So you can have more finer-grained control over the repair through the tool that we have by by classifying fields as repairable or non-repairable.
And you could probably use those unmodifiable as facts to do the further analysis when you get into these kind of situations. Right?
You could, yeah. But right now we don't expect you to write those in the repo K, but the tool directly provides support for saying that, okay, this field should not be changed by repair because I know how I am updating it, and I know it's very easy to update and nothing will go wrong on this. Good question. Okay, so for related work, fault tolerance and error recovery have featured for a long time. Most of the past work has focused on specialized repair routines, and I'm sure everybody has used some of them already. For example, check disk fixes your file system and you just unplug your machine without shutting it down. There have been some commercial systems which support repair. Dembski and Reinhardt, to our knowledge, are the first who came up with a constraint-based repair framework. So they'd find a first-order logic in which you would write the data structure constraints, and then you'd write some mappings between that translate data from this abstract domain to the concrete implementation domain. And then they had a specialized algorithm for which was not a search-based algorithm for performing repair. And in conclusion, we believe we have an interesting view of assertions where you use, and these are assertions written in the code, in the same language as the programming language, where you use a violation of an assertion as a basis of repairing the erroneous execution. We have an algorithm for repairing, which using the optimizations that we have published recently, it seems to work well. It does provide a non-conventional application for a backtracking search. However, still, we are not able to do repair in a very practical fashion. If you have hundreds of thousands of objects on your heap and something gets violated, you are not going to get real-time repair. There will be some lag if it all fixes it. However, we do believe it opens a very promising direction for future work, because now you can have a unified framework for error recovery and software verification. You could do using the same assertions, systematic testing before you deploy the software. Here you use the assertions as a basis of generating test inputs or as a basis of doing runtime checking. And then the same assertions translate into repair routines in deployed software. And here is some contact info and a URL from where you can get the current implementation of the tool.
Any other questions?
Is that the link to the direct? Is that the link to the tool? What's the name of the tool?
Juicy. Yeah.
So at any point when you perform a repair operation, if it fixes the problem, you make that assumption that. So what I'm trying to get to is that what if there's multiple ways to repair a problem? Now, is there there's only one replicate page per data structure. Is that the convention that you use to implement?
Typically, yes. No, typically there's, so replica for these Java programs are the class invariant, so you have one of them.
So is there a possibility that one repair action can actually break the replica in another place?
Okay, so if you have a case where the elements in the nodes of a data structure are data structures, like some complicated data structures themselves, then what would happen is you'd need a really detailed assertion which talks about the entire correctness. So it recursively talks about the correctness of the element, the object graphs that are elements of the nodes. But if your question is whether the search can go into cycles, that cannot happen because it does a bounded exhaustive search and it only considers one possibility once and it will terminate.
Well, what I'm wondering is that if there is, let's say, one inside your replica, you have multiple ways of repairing a point.
Yeah.
So choosing the first one may break your replica in another place, but choosing the second one may not.
Yes. So that's a good question. So, but that will affect the performance. So in particular, you can very easily come up with examples with trees where you have an option of which edge to break to remove the.
Setting to null is a good example because setting to null can fix a lot of things, but it actually can break the size all of a sudden. Like this becomes half as long.
Yeah.
Now, where can you go back and recover and try to say discard null and use the second option? You see what I'm saying?
Yeah. So in that case, if you have fixed size to be unmodifiable, it will come back and try another value for the left or right so that it's non-null and you get that node back. Yeah. So, but you're right, because the basic thing is that, you're only given this assertion. So in a sense, any structure which satisfies it is a repaired structure. So, and of course, there is a lot of freedom.
So, you didn't, in the related work, you didn't show any work on database. And so
okay.
Before 2003, whatever, right? And so how would you?
Yeah. So in databases, at least the ones we looked at, and for example, the only one we looked at, the HSQL DB. So the fault tolerance there was that it would generate logs of transactions, and so that's like checkpointing, and then you'd re-execute the transactions, and that was the error recovery, and that was that's the in some sense, that's very nice error recovery because that that's what was done and that should be done again. That recreates perfectly the state of the database. But I I'm not aware of like this sort of constraint-based error recovery, even in the context of databases. And when we looked at HSQLDB, like we did inject some, we would generate a database with 100,000 nodes, inject some errors in the AVL tree, which is the backbone of the data structure, and then of course the database realizes that something has gone wrong. It re-executes all the transactions, but it takes a much longer time to recreate that database than our repair would do for a small number of corruptions in the AVL tree.
In the database, there is work that's been done, and maybe recently, but to cleaning up data, for instance. So you have old data in some old format, and then you want to reformat automatically to a new format, so you have to clean up the data. So this is perhaps a bit related.
Yeah.
But the other point also, like something big in database is that, and you could do the same thing here, and why not? That's my question. I mean, to prevent the data structure to be corrupted in the first place. So there's a lot of work on database integrity constraint where you have some constraint that you want to preserve, and then whenever you have an update, you block it and you can generate code automatically to check whether or not an update may violate the kind of invariant, so to speak, and if not, if so, you block the update. So by construction, you prevent basically the data structure to ever be corrupted.
Yeah.
Why not about that?
Yeah, no, that's a good point. And you would do these checks. If your assertions are enabled, assertion will trigger off. Perhaps the first time you may do something wrong, but then you might have. So what's the?
So it's easier.
What do you do? Yeah, it's easier in a sense. And what do you do in that case? Because especially if you have a problem like this, that you have some bug in there. You re-execute, you'll get the same thing again.
There's still this picture of like, this stuff is going to fix automatically the database, the data structure, but how exactly? And so there's still, I mean, personally, this is still something I have to
No, you're right. So
fully solve to the ID because
of course.
fixing the data according to rep, okay, whatever. But so, I mean. So
yeah, I agree. That's I said in the beginning that the reason I picked this was because of that issue, and so the contentious nature of this whole business, and but that's why we really want to look look at the issues I mentioned over here. That perhaps can we define like some concrete characterization or some crisp characterization of exactly what guarantees are you giving. And so far what we do is, like at least what our implementation tries to do is it preserves the reachability of the data elements. So if you start with the binary search tree, you'll end up with the binary search tree which had the same elements that the original one did. So that's all the guarantees that we have. But we would of course like to have a crisper characterization, but we are working on that and we don't have solutions for that yet.
Okay, thank you again for
Yeah, you're welcome.